Good morning and welcome to this course on distribution theory and Sobolev spaces. It is named as advanced PDE, but in the part 1 of this advanced PDE, we will be discussing more on distribution theory and Sobolev spaces and maybe very little on the weak formulation, but that is the major part of the second course. So, having introduced the minimum basics required, we move now to the minimum basics in the about the LP spaces and some measure theoretical things and then of course some important locally convex topological spaces. Now we move on to mainly the main theme of the course, mainly distribution theory and Sobolev spaces. As mentioned in the introduction clearly, we splitted this course into two parts. It is actually a one semester course both together, but we have split into two courses of 8 weeks each, is mainly for the benefits of the students. Each course will have 20-hour lecture and consisting of 40 lectures of half an hour, and essentially or on an average 5 lectures per week on an average, each lecture of half an hour. So, basically you have to study approximately 2.5 hours to 3 hours. As again repeat, you may not see much PDE in this first part, and this idea of giving this one is twofold. One, this first part will be useful not only to the PDE people who are studying, it is also useful to other mathematics students, especially when you study certain topics in topics of analysis. So, after this first course, students will be ready to take the second course. Since it is a crash course, it may not be easy to grasp the idea, because this is a really consists of very new ideas and it is not very easy to grasp the ideas. You need time, and because these ideas are quite different from the analysis of functions, you will be dealing with the new objects which are not really familiar to you. So, it is advisable for you to fix these ideas. So, spend some time even after the first course before taking the second course. And some comments to begin with. The theory of distributions has completely changed the study of PDEs after 1950s. Of course, though it was introduced in the 1940s by Lawrence Schwartz, you will get to see more about it. The necessity of such a fundamental theory was inevitable, was evident from the development of PDEs prior to 1950s, starting from the beginning of the 20th century. So, it is introduced. It is also nice to remark that, and it is interesting to observe that the Sobolev spaces, though quite often we study after the introduction of the distribution theory, actually was introduced in the 1920s before distribution theory. Of course, that somewhat formally requiring a more stable foundational theory to understand Sobolev spaces. So, my aim in this first lecture is to give a lot of motivational examples why we need distribution theory and Sobolev spaces, and we try to start with, before formally giving, we give examples of a kind of introduce a notion of weak derivatives of non-differentiable functions, a different notion of solutions of PDEs called distributional solution, and perhaps though it is very advanced thing, a new concepts, and this concept of weak solutions are more closer to actual physical solutions, and these things we will do before getting into the formal definition. So, if you it is well known that many of the physical quantities quite often need not possess smooth solutions, like continuity. Smooth solutions means a property of functions like continuity, differentiability, etc. This is due to the physical reason that we may be modeling physical systems and the physical solutions, physical quantities may not be continuous at all, it may be discontinuous it to represent the actual physical quantity. On the other hand, modeling of physical solutions lead to differential equations whose solutions are physical quantities. So, this is a kind of a dilemma, and but differential, because differential equations require smoothness of functions as solutions according to the order of the differential equations in the classical sense. Thus, if we are searching for solutions in the comfortable class of smooth functions, we will not be able to get the actual physically relevant solution. This forces us to look for non-smooth functions as or even other objects which are not familiar to you, and you are going to get to see such objects in the next 20 hours in this course, basically giving a differential equation uses. So, you basically probably interpret the solution of these two differential equations not in the classical sense, but in a more generalized sense to get non-differentiable functions which may represent the actual physical solution. So, let us start with a very simple example of doing it from ODE which you are familiar to you. Okay. So, start with an example here. If you want to see more about it, see our book on ODE. ODE book is explained a lot about it, book by us, PSD and Raju K. George for this example. So, let us look at a first order ODE. How does a first order ODE looks like? Y prime is equal to f of s, y of s, ds with y at 0 is equal to say y naught. So, this is an equation we want to call it star. But then if you integrating you get yt is equal to y naught plus integral 0 to t f of s y of s ds. You see, this we call it a star. Now, look at the equation double star, the second equation. This does not require differentiability, does not require differentiability, so you can interpret even a continuous function as solution to this one. So, I will not give you the details, but when f is continuous and a continuous function y is called a solution if it satisfies the star. Okay. But if f is continuous, you can do some interpretation of that, and then you can see that indeed y is differentiable and then y satisfies star. So, star and double star are equivalent when f is continuous, but there are physical situations like in controllability and many other situations where you can interpret a continuous function as solution to double star, that is called an integral form of the differential form star. The second one is called the integral form, the first one is the thing, and you can interpret. So, such a solution is called a mild solution, especially in control theory and other places. So, you see, you can interpret a continuous function, of course, in the case of discontinuous f, a continuous function y as a solution to the differential form if it satisfies the integral form. So, you see, and so such things in examples it does exist, we do that one. Okay. So, more details about you can see it in your equation. So, let us go to the now another example 2. So, we will have a example 2. So, I am going to give you a lot of examples in this course. You consider a very simple equation, first order equation du by dx equal to 1 with u at minus 1, u at minus 1 equal to u at 1 is equal to 0. That means you want to solve this equation minus 1, 1, 0. Okay. So, you want this solution u to be from starting from here, and then if you want here, you want some solution here. So, what I want to give it as a small exercise here, there does not exist any smooth solution. It is a very simple example, because when you want to do that way, you can see that actually u vanishes at some point and you cannot have more du by dx equal to 1. Any solution u in C1 of say minus 1 to 1, you cannot access it. But so if you relax a bit, suppose I wanted you are going to relax little bit on the solution. So, looking for a solution u, relax a bit, looking for u which is continuous. So, we will do that, which is continuous but differentiable except at a one point, but differentiable except at a point. So, see, so what you are going to do is that, so you have this thing, okay. Okay. So, you have 0 here, minus 1 here, 1 here. So, if I have this one, so if I have 1 here, this is 1 here, I can connect this. So, see. Okay. So, this is differentiable except at the origin, and then all other places this is exactly mod du by u prime equal to 1. Here also mod u prime equal to 1. This is basically such a u is Lipschitz continuous. Okay. So, you see, the moment you relax a bit, you are looking for a solution which is differentiable except at one point, but then thing. Now, you can relax little more, actually you can get more solutions. For example, you see I can get minus 1 here, 1 here, and I can construct this one. This is also a solution now, you see. So, that moment, the moment you relaxed a bit, you just relaxed to differentiability except at one point, and then in fact you can ask questions, does there exist solutions which are C1 except at finitely many points. So, if you relax such kind of thing, you can construct, you immediately you lose your smoothness and you get many solutions. So, the relaxation you have to, when you are relaxing and looking for weak solutions, this is one of the major issue. You may get solutions, it is not only bring you your actual physical solution, it also may bring other solutions which are not really physical. So, relaxation of conditions one has to do that one. For example, if I want to do this one, I can go half here and I can come here, I can do this one, I can come with that. So, this is not differentiable at all these points. So, you have, if you relax that finite, if you relax with finitely many points, I can construct infinitely many solutions, infinitely. So, I am trying to also tell you not only the example where you do not have smooth solutions, I am also giving that when you relax it infinitely many solutions. Okay. So, this is actually this example is a special example, the above example. The above example is a very special case of a class of equations known as class of equations known as Hamilton-Jacobi, known as Hamilton-Jacobi equations, or Hamilton-Jacobi Bellman equations. This is a Bellman equations. This is coming from calculus of variations or optimal control theory. Optimal control theory. So, but let me also remark that the theory which we are going to introduce, the theory of distributions, are not suitable to study this kind of, these are all very general nonlinear partial differential equation. So, we will not be discussing this one, but if you want to see, again we give you as a reference of our PDE book. This is what we have done, PDE book, classical theory with a modern touch. So, this book by two of us, AK and PST. More details are given here, introduced here in this one. Okay. So, so you can get into that equations. There you will have, so you may need to give additional assumptions. So, let me give you another example now. Example probably 3. This you would have studied already, first order PDE, okay, and especially in the case of quasi-linear equations, quasi-linear equations. Okay. So, typically a quasi-linear equations develop what is called quasi-linear equations develop singularities. You may have a very nice system of equations, and you may have a very nice system of in a nice initial condition which can even be C infinity. So, initially you may get some nice smooth solutions and suddenly it can develop singularities. Of course, these singularities are physically relevant singularities. Such singularities are called shocks. So, in a physical situations, shocks can appear. Okay, so how do you deal with again equations with the actual physical solutions called? So, typical equation is called what are called Burger's equation. Equation ut plus ux equal to. So, I am not giving all these details. If you want to understand, can look into our book, and this one ux at 0 is equal to u naught of x. This is a typical quasi-linear equation, and these are all special case of another theory, just like Hamilton-Jacobi equations I told earlier. This is a special case of conservation laws, which are given in our other NPTEL courses. Okay. So, it can develop what are called singularities, which you are. So, in this first course we develop, the first course we develop the notion of weak derivatives to understand which requires the theory of distributions, and we also introduce appropriate spaces. So, you basically understood the necessity of developing such a theory through these couple of examples. We will tell you more about it, and known as Sobolev spaces, the functions to study the weak solutions. Of course, the weak solutions in more detail we will study it in the second course. So, the first part of this course is to prepare you for the second course, where you will see the analysis or calculus developed on objects which are not functions. We will do that. So, let me, the new objects which we may introduce are called distributions, basically which are linear functionals on a class with appropriate topology. So, you have to have two things. One is a class of functions known as test functions, for which you need a appropriate convergence. Basically, you need an appropriate topology, and this is how you have already seen it in your introductory lectures. Okay, so, in the introduction we will give you already given, have been developed. Okay. So, there are actually various types of weak solutions introduced in the last 100 years or so, kind of distribution theory, transpositions, solutions by distribution, transposition solutions, entropy solutions, viscosity solutions. For the equations with Hamilton-Jacobi equations, you, as I said, the distribution theory may not be such general nonlinear equations. The distribution theory may not be the right theory to study, for which your viscosity solutions are more suitable. But among all these theories, probably the notion of weak solutions in the sense of distributions and also the interpretation of weak solutions and Sobolev spaces took a center stage after 1950s. The important thing is that this whole theory subsequently changed the entire scenario of studying partial differential equations. So, the 1950s, in the beginning of 1900s, it started these ideas, but then it emerged, becomes a topic of functional analysis. So, the PDE presently treated as a topic of functional analysis. So, let me begin with one more example. Probably this example I think I will be able to cover, and then so we will have one more example, and then more we will start later. So, these couple of lectures, not only couple of lectures. So, let us call the Dirichlet energy function. This was introduced probably in the after 1850s, if I remember correctly, Dirichlet functional. Some more motivation for my distribution theory. F of v is equal to half of integral of grade v square omega. You can think it as a function domain in Rn, bounded open set in Rn. So, this is the energy functional. Okay. This is an energy. Specific cases may be straight energy and other things. So, I do not want to get into all that detail. So, what is the problem? Minimization problem. You look into the problem of minimization. You want to energy minimizer. This we call also energy. In practical particular or specific cases of applications is indeed energy. Okay. So, you want to minimize the energy for an elastic system or whatever it is. So, what is the problem? So, find u in some space. Let us see whether we can choose something. You will see that some space such that u is the minimum energy in that is equal to minimum of f of v and v is in x. So, how do we proceed with this? So, let us call this to be alpha, say. The thing is that you want to find u and that alpha. So, alpha is the infimum basically, alpha means infimum of f of v, and we want to show that that alpha is achieved by some solution u. How do you go about it? So, what are the minimum things as soon as you see the problem you want to set up something. How do you choose some suitable space x? One way you want to have integral of grade v square. So, you want to have that f v to be finite, that is the first condition. So, for that we need minimum, we need we need that v to be in some C1 space, means it should be differentiable and integral. Of course, you can relax it and that is what we are going to see later, but at present we do not have a new theory. In a classical setup we need C1 of omega, and to avoid the boundaries, so you take the C1 as up to the boundary, because if you do not have the continuity up to the boundary you may not be, again the integral need not be finite. And these spaces we have already seen in our introduction, seen in our preliminaries. Okay. So, what is the kind of thing I want to look? How do you study a minimization problem? So, the idea is to look for a minimizing sequence, that is a naturally thing. So, look for minimizing sequence. What is the meaning of minimizing sequence? This is what you have studied. How do you solve it? For example, let me think minimizing sequence Vn in x. This is x, and this is embedded with a smooth norm which we already discussed, C1 norm, smooth C1 norm. You already know this space, because. So, how do you choose a minimizing sequence such that your Fen converges to alpha? This of course is a kind of vague description. So, you look at this, I am sure all of you know this exercise. How do you solve this problem? Suppose I want to solve this infimum. Suppose f is a continuous function, f continuous on AB. I want to find an x such that f of x equal to minimum or infimum where y is in say interval AB. How do you solve this problem? So, this method of looking for minimization, I am not given f to be here differentiable, only continuity. How do you look for it? You call this to be some alpha and then look for yn in AB. So, this is a standard thing. So, you can look it as an x, work out the details such that f of yn converges to alpha. Then what do? You want to get the convergence of yn, that is what you are looking for. You look for convergence of yn. You need properties on AB, that is a different thing. Okay. Convergence of yn may be along a subsequence such that yn converges to some y. This is the first question you have to address. Okay. So, you have to get the convergence of yn, and for that you need the kind of topology there. You need to use the properties of AB. Okay. And then the next question is that, is this y belongs to AB? That is the second thing. Okay. And then the third question is, does Fyn converges to f of y? That is true if f is continuous, I already assumed. So, you see, you have a set of things for a minimization problem to be solved. Complete these simple exercises. So, I am not going to do this problem, I want to see the difficulty when you deal with it. So, you want first you look for a minimizing thing which you access all the time. So, you want to see Ft. So, how do you address these questions about the convergence in Vn? Okay, convergence of Vn. So, convergence of Vn. For one of the things to convergence of Vn, probably you may need some uniform convergence. That is what C1 will provide you. Can we get this uniform convergence? Then probably uniform convergence. Then probably Arcila-Ascoli or some type of theorems probably you will be able to apply. The issue is not that Arcila-Ascoli. The major issue is that how do you get the convergence? Convergence has to come from the data, just like in this case Yn AB, the convergence has to come from the knowledge of AB or knowledge of, but you are here dealing, the norm is in C1, this is the major issue. C1 has a smooth norm, and but you are minimizing an integral. So, you can only get some estimates based on integral, you cannot get based on uniform norms. So, the obtaining a uniform norm in C1 may not even be possible. Okay. So, at the most you can it may be possible, it may, so that is what Levy observed, not only Levy, many others even in 1906 observed this fact. What he has eventually said that you need to work with integral norm, that you need to work with this type of norm on this space C1 of omega bar. Okay. So, then with respect to this norm, this space may not even be complete. You see, with C1 norm, it has its own supernorms, which is a complete space, the completion. So, you have to look for a completion of this space. Okay. When you look for this completion of this space, how do you understand what is this space? What is this space? What is this space? Okay. So, I will discuss little more about this one, and then I will go to another example, especially from the Dirac delta function in entirely a new objects. Of course, at this stage I cannot understand this properly, but I will explain to you little more about it, and we will stop here in this lecture. Thank you.